This lesson is about magnesium number 12 Mg. Magnesium is over here, number 12 after sodium that we saw in the previous lesson. And the big question is, can we detect magnesium with our handheld XRF spectroscopy system? In the previous lesson we saw that we can't see sodium. Our system, these handheld systems in general, they work in air. So here there is just normal standard air, and air will stop low energy X-rays. From our table we see that the energy of the sodium XRF line is 1 keV. From this online tool we can calculate how many in percentage of these X-rays from sodium at 1 keV can go through 1 centimeter of air. So we input these parameters over here, and what we get is just 1% of the X-rays can reach the detector, can travel 1 centimeter of air. We did some experiment and we noticed that there is no way we can actually detect this 1% because we have the noise of the detector itself. Let's see now about magnesium. The energy of magnesium is 1.2. So there is a 1/4 more energy in respect to the sodium. Is this a tiny bit more energy of the K-alpha line enough to be detected? Let's check with the software. So we input over here 1.25, so the energy K-alpha line of magnesium, and we see now that the percentage is changed a lot actually. So we have that almost 10% of the magnesium X-rays can reach the detector. So definitely we have hope that we can detect magnesium. Let's go to the lab. We start with our standard of magnesium cube in a metal form. We put it under the detector, and for this acquisition we will apply the no filter setup. We want to look at this peak that is at 1.25 keV. We are in the range 0 to keV. Definitely the best way to operate is to remove any filter from the collimator. Right now the collimator doesn't have any filter, okay, so we can use as it is. We put the cube over here, ready to acquire magnesium. At 1.25, actually to be precise, we have a relatively intense peak of magnesium. So we were able to detect it. The photons can reach the detector in a number that is sufficient to be more than the noise of the system. Let's try something else. We try this object, a pencil sharpener. These pencil sharpeners, generally they are made of a magnesium alloy. So there will be aluminum, in particular the main component, maybe zirconium. It's very lightweight. When you hold, you can tell it's magnesium because it's very light. Okay, let's measure and let's see what we get. And there it is, the spectrum of the pencil sharpener over here. We see that basically now the peak of magnesium is the same of that of the pure cube of magnesium. This is because the sharpener is an alloy of magnesium containing other elements. In particular, there will be aluminum, so we see the other peak over here. So far, when we have magnesium used as a metal, basically we can tell it very easily. Let's see what happens with a mineral. Magnesite. This is used for rock climbing. This material is a magnesium carbonate. Let's test it out with our spectrometer. This is the spectrum of magnesite that we'll analyze in the lab, and we see now the difference. You see now the spectrum of the magnesite, the peak of magnesium is just over here. So since of course the concentration of the magnesium atoms is much less. There is one atom of magnesium, but also there is one of carbon, and there are other of oxygen. The concentration is less, and consequently we have a lower peak for this mineral containing magnesium. Now we test this green mineral. It's called celadonite. It's similar also to glyconite, and these minerals are the main components of green earth. So these are pigments that has been used forever in art, from basically antiquity to recently. It's used and it's found natural. So let's try this mineral. This one is the peak of celadonite. There it is. So celadonite again is the main component of basically what we will see the green earth. And of course here from the formula of the mineral we see that its concentration of magnesium is much less. Consequently, the peak that we have of magnesium start to be basically undetectable, barely visible, almost comparable to the background. Eventually, let's try an actual pigments containing magnesium, green earth. Using a pigments checker, let's now check the spectrum of green earth. So we have it over here, and we put green earth under our spectrometer. This is the spectrum that we acquired from the pigment checker, the green earth. We see now that the peak of magnesium compared also to that of the celadonite, basically you see it's the same thing, is very low, is barely detectable. I will conclude with this simple table. We have sodium 11. Sodium is not detectable because of instrumental limits. The distance of the target to the detector, 1 centimeter, is too much. So we can't detect it because the photons can't reach the detector. Magnesium is detectable because it has a little bit more energy, but just when it is in large concentration, like as a metal. When it starts to be present as a mineral, in particular in minerals for pigments, celadonite, glauconite, in that case basically we can't detect it, and the issue is concentration over here.